Hello, my friends. This is William M. Briggs, and welcome to episode 42 of Uncertainty and Probability Theory, the Logic of Science. Today we're going to continue our discussion of cause. Cause is our goal, the discovering of why something is, how it came about, what it's made of, what shape it takes, what form it takes, and the purpose of things. This is the full cause of everything. And unfortunately, we have this little bit of a twist, this determine or deterministic. The word is unfortunate in English, as we're going to see. It has two meanings. And the sin or the fallacy of equivocation often crops up when we're not careful about using the word in its proper sense. We can start out using it one way, switch to another halfway through our argument, and switch back and not recognize what we've done. Equivocation is a very common thing that happens, of course, that goes wrong in philosophical arguments. Now, let's talk about a causal model. Let's suppose we're interested in some proposition y, whatever that might be. We're going to give some examples here. And we have a collection of premises, however long, completely compound list of premises. This can be acres long, including all of the implicit premises, which includes the definition of all the words, what they mean, the punctuation, grammar, every implicit and tacit premise that goes into some knowledge of cause. And of course, if we're interested in the probability y is true given this cause, well, it's either going to be it's going to be in the set 0 or 1, depending on the particular conditions. That is a causal model. This is a model of y given this cause, and it depends on exactly the situation of exactly what y is, the statement about y. Either that's going to be completely true or it's going to be absolutely irrelevant. The third thing is no probability, or we deduce it's the entire range of 0, 1. If this is absolutely unrelated to cause, the conditions, I'm going to give you some examples. But we did all this. This is review. If y is, so for instance, this is a causal model of how a steam engine works or something like this. And this is whether or not you out there, you the viewer, happens to enjoy beer. Okay? Well, the two are unrelated. However, we can gather from the implicit definitions of the words used and so forth that this is in a contingent. Remember, we did contingent last week. It depends on the way the world is. It's not necessarily true or false that you like beer, especially given knowledge about steam engines. And so in this kind of a case, we have absolutely no probability at all except to say the thing is contingent. And in fact, in this case, we need to use these soft parentheses right here because it's not absolutely certain and not absolutely false. It could be anything. Okay. Now let's give some examples right here. I'm going to give you a better model. But our goal, though, is if we're talking about a steam engine and we're talking about the knowledge of a steam engine, and we're asking about a particular thing, will the steam engine produce this much torque under certain given conditions that we have in here? That's going to be either true or false if we have full knowledge of the cause. That's what we're after in all of life, is trying to figure out the cause of things. And for most things, of course, we're always going to remain somewhat ignorant. We're never going to have the full causal explanation of things, as I'm going to kind of show you here now. Okay, suppose we have a model. Then let's have a model. Let's have a model in which says this: the object, whatever the object is red at time t, otherwise it's blue. Okay. So there we go. So now we want to know whether or not, say, the object is red. Well, the probability that it's red, just given m, we have no knowledge about what t is at time t is here, is we can't tell. we cannot tell whether it's anything because we don't know anything about it. All we can guess is, again, this is a contingent event, so that this probability is the whole interval. But suppose we have at time t right here. We say and, we can do union. We could write m union t. We can write m, and t, or just mt using sort of Boolean notation mt. Well, then the probability is 1. Simple as that. If it's not t, if we want to do like a contrary, well, then the probability that y is red, the object is red, is 0. So here's our causal model. This is not a causal model, however. This is a deterministic model. This is a deterministic model because we can determine the color from this. But we want to ask further questions. Why red? Why blue? Why time t? This model does not tell us. It does not tell us. We do not have the full cause. We do not have the full cause. And remember, for the full cause, we need to have all 4 elements. We need to have the efficient cause, what made the thing, the material, what's it made up of, the formal cause, what shape does it take? This could be applied to absolutely anything. And the purpose, the end, the final cause, the teleology of the thing. What's the thing for? That's wrapping it all together, wrapping it up all together. We need to know all 4 of these things. For this particular thing, we don't know what the object is made of, but we do know the form it's going to take. It's going to be either red or blue, but we don't know why. We can determine with absolute accuracy with this model. We can calculate a probability with absolute accuracy with this model. We can determine the value of y, but we don't know the cause of y. So this is the problem with the word determine. Determine could mean either the state, to say what the state is, to know, I guess we can either know, or the cause. We could say we say that this is going to determine your fate, your choice. So your cause is going to determine your fate, and all of these other causes are going to operate. So we can mean it in a causal sense or a knowledge sense, determine. We have to be very careful about this word determine. We see it all the time in science. So we have to ascertain exactly what's going on with it when someone says we have a deterministic system. A deterministic system can tell us what's going to happen, but with absolutely no knowledge of the full cause. All right? So when someone said that's going to determine, we figured out something that's going to determine somebody's behavior, it doesn't mean a cause is involved. It can only be knowledge. In other words, the claim could be entirely epistemological as opposed to ontological. So let me write that up there because you're supposed to write what you say. This could be entirely epistemological, a deterministic model, or it can be ontological. And this is the big separation we've been talking about from the very beginning. The confusion between the epistemology of things and the ontology of things is extraordinarily common, and we absolutely need to keep these things separate. Okay, now we can modify this model, obviously add to it, adding all kinds of things, but that's not the point of this particular model. So let me give you just another example, because I have it in the book, and I'm going to give an excerpt of the book. The homework will just be reading this. So, here's a sucker. Or a lollipop. We call them suckers in Detroit. I don't know what you guys call them. A lollipop. I'm pretty sure most people call them suckers. But not everybody. I mean, a lot of you guys say soda for this word, for pop. But here in Michigan, anyway, we say pop. Okay. All right, so this has it has all these 4 causes. The efficient cause is whatever the machine is that made it, the process. The material cause is sugar, dye, whatever, maybe flavorings. The form, of course, is a lick on a stick. And the end was to produce a piece of candy. Now, if we had all of this in some kind of a seed, and we were going to ask questions about this sucker, we could answer those questions fully. All right, we could answer those questions fully. We'd have a full causal model of something like this. But lacking any of these, we don't have a full causal model, and so we can't answer all questions about this. Now, in nature, of course, we often only know fragments of things. So let me just give you an example. So here's an example of non-contradiction. We did this before. Given our intuition, our inductance, one of the highest form of knowledge, the induction, we talked about has at least 5 different kinds, and the highest form of induction we have is the induction intellection. We used our intellect to infer this probability of non-contradiction. So we say that is true. The probability of the non-contradiction is true, that statement, that logical statement, given our induction, our intellection, is 1. But again, we don't have the full reason why it's true. Why is the universe set up such that the principle of non-contradiction is true? We don't know. We accept that it's true. We accept many axioms, right? Remember we did all this axioms business before. We accept axioms as true. We have some evidence that goes into them, but why they're ultimately true, we don't know. A lot of nature is just closed off to us and always will be closed off to us. We have to take this stuff on faith. There's no argument of getting around faith. You could try, but you can't. If you're using logic at all, and you want to use logic to make arguments of any kind, that the rules of logic are true, you can't prove. You have to assume them. You have to take them on faith. Math, everything flows from this. We did that a long time ago. Okay, but this is just to show you, and of course we'll meet lots of other things later in science that shows us nature is closed off, like in quantum mechanics and so forth. We often know. Okay, so all right, let's give more examples here. The difference between determine and cause. Last time we did y, we had a vase. So we have our vase now. I gotta really fix this board so it sticks. And then we had x, ball hits. And so we have the probability that y is true, given x equals 1. Remember we did the baseball hitting the vase, and that's an event that is not the baseball hitting first, and then the vase breaking. It doesn't happen that way. Although you'll see accounts like this all the time in science. It doesn't work that way. What happens is the ball and the vase are in one simultaneous joint event. The ball going through the vase and the vase breaking is all one thing. It's not separate, loose in separate things like David Hume said. It's not the case at all. It's happening jointly and we can see it. Now, is this always going to be the case? I'm asking this question to you. Is this always going to be the case that a vase is going to break when a ball hits it? Obviously not. So part of this, x here, has to be the conditions. The conditions that allow this ball to bring about its power of breaking a vase. And so because the cause can be in here. The cause, the efficient cause of the ball knocking through the vase can be in there, but we don't necessarily have all of the conditions. All right. So in order for a substance to use the powers that it has, the conditions have to be in a certain way too. So we often talk. I often talk, and we're going to learn this next week. We're going to go through this more carefully. I call it the causal path. To see what's going on, we have to know the full causal path. We not only have to know all this stuff about a cause, but we also have to know the conditions that can bring things together. So all that has to be part of what we're going to know. All right, let me give you even a better example of determine versus cause. All right, this is more sciencey. Here we go. People love math. So here we have. People don't love math, but my listeners like math. So here is an equation for an object launched with an initial velocity v0 or v0 at an angle with respect to x of theta, And I'm going to give you the equation that determines the height of y. All right? So this just happens to be times x minus g times 2vo squared. Oh, I'm going to have to erase this business here. Cosine squared theta all to minus 1 times x squared. Okay, that just happens to be the equation that describes this curve. Now, theta is, of course, this angle. That's a given. G is a constant, and it's a given. G is, of course, a gravitational constant in this particular case. V, or V naught, is a given. And, of course, X is a given. For given values, the model can be said to be a function of theta, G, V naught, and X, or V0, whatever you want to say. The probability that y equals y, some little y that we're going to have here, given this model, is again going to equal, I ran out of board space here, or 1. I hope you can see this. Given this particular model, which is just a simple function of this angle theta, this value constant of g, this initial velocity v0, just these numbers, and x, the probability of y is at any given y, given these things is either 0 or 1, depending on whether this y meets this equation or not. Simple as that. So we can with this obviously with this simple example right here, we can class all science as probability. In the epistemological, this right here is trying to say something about the ontology. We're going to come to that in a second. This part of it right here is the epistemology of it. How do we know what's going on here? All right. So this is a deterministic model. We'll hear this kind of thing all the time. You'll hear physicists talk about this kind of thing. It's very simple mechanics. Well, it's mechanics anyway. It's not very difficult to deduce something like this, and it gives us some idea of the cause. But it doesn't tell us the full cause. This is not, in fact, a causal model. We don't know where the G comes from. We don't know what forces are propelling any of this. This is just telling us what's happening with Y. There doesn't tell us why a particular thing has to be where it is when we say it's going to be where it is. All right, it doesn't give us the full causal determination. So why is this particular value or not? We don't know. We could tell partly, but we can't tell the full cause. We need, remember, we need the efficient cause, the material cause, the formal cause, and the end. We need to have all of that in order to say something. Okay, so let me give you a little teaser here. Suppose we're doing this, we're scientists, and we're measuring. Oh, look at that shadow. Suppose we're down here, we're measuring. We did this with real objects. So there's our baseball. We're going to launch our baseball. Here's our bat. Does this look like a bat to you? Anyway, and here's the baseball knocked at an initial thing, and over here somewhere is our base. All right. So here's the baseball knocking it like this with an initial velocity of something and so forth. So we can tie this back to our base. Tie this back to our base example. So suppose we're doing this in real life. We're going to take real life measurements of this, and we observe. We accept this equation. We observe. Can you see that? Let me try to make this a different color. Here it is right here. At this particular value of x, instead of that, we have this. In other words, y is instead of y equaling y, we have y equaling y minus some small number. Now the probability that this is true is 0. I want to emphasize this. The probability that y at this particular, I'll just call it mx, and I'll call this epsilon x just to indicate we're talking about this particular situation. We said this model applies to this real baseball going after this real base right here. And we made this measurement. It's some tiny amount, doesn't matter, fraction of an inch. fraction of an inch. It's not y, it's y minus some epsilon at that particular value of x. It doesn't matter if it matches everywhere else. It could be, the baseball's actual flight could be here. For some reason here it took a little dip and then got back up somehow, gust of wind, something. See, I'm pointing to cause there. Anyway, but it bounced back up and it went on its way. Now, this is true. It is true that the y will equal y minus epsilon given this particular model is 0. So what have we done? We have, you're going to love this. This is one thing I don't like. Falsified. We have falsified the model. The model has been proven false. There's no getting around this. We have proved this model false. But of course, it's absurd, but this is what people like Karl Popper, he came up with this idea of falsification in science. We have proved that this model is false, but no physicist is going to abandon this model. They're not going to toss this model away. And why? Because we accept a little fuzz. We accept that this model is deterministic, not fully causal, but deterministic. And what we're going to really allow, is we're going to say probability of y is about equal to y. We're going to allow some fuzz. We're going to allow some fuzz. This is fuzz. And the fuzz depends on the decisions we're going to make based on it. In other words, we're going to allow, we're not going to say we're going to be exactly at y. We're going to be at y plus or minus a little bit, whatever. It's close enough. Close enough, right? Close enough means we have, in fact, falsified the model. We have said the model said it is certain that y will be at y equals little y. It wasn't there. It was, in fact, here. Therefore, the model has been falsified. But we allow fuzz. So this model now turns into a probability. This model turns into, we don't have to allow fuzz here. We can do it like this. This would be something like just high. We could say y will equal little y, given this model. We'll just give it right there. Is high. Some high probability that's not exactly equal to 1. That is, in fact, less than 1. So that's where we're going with this. Falsification of models is extremely rare. It doesn't happen. Scientists almost never abandon models when models make mistakes. They make all kinds of excuses for them. Falsification is going to turn out not to be an interesting thing, but people still talk about it all the time. And in fact, what the real thing that we're missing here is something caused this departure. All right, something that's not in this model, if we accept this model as true, caused that little departure there. What? Well, I kind of hinted one idea, maybe the wind or something like this, or the spin on the baseball, or any number of things that we could posit or something like this. In other words, we try to seek for the full causal explanation of the thing, and not just what determines it. All right, so that's it. That's all I'm going to do this time. And next time we're going to get into the very difficult thing of paths, the causal paths. And this is going to turn out to be an enormous importance, especially when we do a time series of any kind, mostly the accidental time series. Remember the difference between accidental and per se time series? Per se time series were the things that were happening right now together, simultaneously. Not instantaneously, but simultaneously. The ball hitting the vase, and one billiard bar hitting another, one electron whacking into a screen, whatever. Those things are per se time series. They're happening in time. And then we had the idea of the accidental time series, like a stock price or a temperature change or something like this. We're going to talk about all that. All that stuff's going to become incredibly important for that. All right, that's it for now. Go to wmbriggs.com or wmbriggs.substack.com for more. And the written lecture will be at those places, an excerpt from Uncertainty. That's it for this time. Thanks very much for listening.